Thank you so much. Yeah, my name is Will Benton, and I'm really glad to be here this morning. Good morning, thanks for joining me. I'm going to spend this session telling you about how to get started implementing machine learning algorithms for scale-out parallelism. We're also going to talk a little bit at the end about scale-up parallelism, but really the focus is going to be on using scale-out compute frameworks on the JVM like Apache Spark, and we'll have some details about Spark in particular. This talk is going to have a mixture of high-level concepts and code. I assume that we have a lot of Scala programmers in the audience. Is that a safe bet? We have Scala. Who here likes Scala? I've also used some Python. We have anyone who likes to use Python? Okay, so I hope did I not? Does anyone not really like Scala or Python? I'm sorry. So I was hoping I could get a big cross section of the sort of data community who are putting things into production on the JVM. But also, in some cases, it's easier to illustrate a concept on a single slide with Python. In some cases, if I'm talking about the type system, I'm going to illustrate something in Scala. I'm not going to use esoteric language features without explaining what they are, though, so I hope that the code is comprehensible to everyone. If it's not, let me know. So how many people here use some kind of compute infrastructure on the JVM in production? Okay, a few of you. Any Spark users? Flink? Something other than Spark or Flink of people who are on the JVM? Okay, so my assumption is that a lot of people sort of do prototyping in a rich environment like scikit-learn or RStudio, and then later we'll sort of work with application developers and machine learning engineers to put that code into production on the JVM. And this sort of points to one reason why you might want to scale these techniques out. The libraries that you're going to use in scikit-learn in a Jupyter notebook, the libraries you're going to use with RStudio, are going to be more flexible than the libraries you have in an environment like Spark. Like MLlib is great for scaling out, but it may not have the same functionality that you need. And maybe you have something that's close, but it doesn't have the split criterion you want or the distance metric you want. So you need to sort of extend that. Another reason why you might want to implement your own techniques is maybe you've read a paper and you're inspired to try something out, but you don't have an implementation of it that you can try on a lot of data, right? So you want to be able to scale that out and try it. A third example is maybe you do have a technique from an environment like R or Python data community that you're really interested in scaling out and running in production. Well, you can easily delegate a technique like this to your JVM compute framework and have it run with some glue code, but maybe you want tighter integration and you actually want the implementation itself to scale out. So we're going to talk today about the problems you deal with in doing that. My motivation for doing this is that a couple of years ago, I wanted to see if a particular technique called self-organizing maps, which is sort of an old neural network technique from the 90s, could be used to find anomalies in infrastructure logs. Now, it turned out that it could, but in order to answer that question, I had to have an implementation of self-organizing maps that I could run on all these collected logs from a data center we had at work for several months of log data. And I needed to be able to scale it out so that I could get this done and still feel like I was making forward progress on my work, right? So I had to implement these in Spark in order to get this done. So we're going to talk about some of the things I learned along the way. We'll look at Spark's parallel collections, the resilient distributed data set, and for those of you who haven't used Spark, we'll sort of provide some context so that makes sense. We'll talk about what things make programs hard to parallelize and how to work around those, and look at the problems involved in taking a serial technique from a paper and turning it into something we can scale out. We'll then look at how we use some of the more modern APIs in Spark, the kinds of things that users want to interact with more than these sort of low-level interfaces. And then finally, we'll talk about some things you might want to worry about in terms of best practices for using Spark, and also best practices for making sure that your code can actually benefit from parallelism in hardware so that you can have scale-up speed-ups on a single node. And this includes things like using SIMD instructions in a native library, like SSE or AVX, or using GPUs. So I want to start, though, with an overview of the self-raising map technique. The self-raising map is not the focus of this talk, but it's the case study that we're going to use, so I want to make sure that it makes sense. Self-raising maps are an unsupervised technique for producing a discrete and low-dimensional representation of a feature space. The idea is that you want things that are close together in the feature space to map to cells on your map that are close together in the map. Now, maybe that makes sense, maybe it doesn't, but let's see a video of what it looks like to actually train one of these. So we're starting off with a random map of colors, and we're going to train it with random color data. And the idea is that we're gradually gonna go through each iteration of training the map, and you'll see even on the projector, this can get a little washed out on a projector, but you'll see how we start sort of random. We go to this sort of desaturated thing, and then as the training progresses, you start to see more identifiable areas of more and more saturated color. And the way I'm comparing color, for those of you who think about this kind of thing a lot, is I'm just using angular similarity in the RGB space. So that's why you see some sort of differences in value of the colors. So this actually turns out to be pretty simple to implement online if you want to look at one sample at once, if you want to do it serially. And the idea is that we just start with a map. Here we have a map that I've initialized arbitrarily but not randomly. This isn't the only way you could initialize a map, but we have an initial map here. And we're going to look at an example. And when we look at an example, we're going to find the thing in the map that's closest to the example, which we're going to call the best matching unit. And then we're going to take the map and we're going to adjust the values in the map so that the best matching unit and the neighborhood of nodes around the best matching unit get closer to the example we saw. So we'll impact the best matching unit the most, and as we get further away, we'll have less and less of an impact on that part of the map. So that kind of makes sense, right?
So what is the problem that we are trying to solve?
We're trying to go from a random map to a low-dimensional representation. So in the color example, we went from random colors to a place where I said, well, in this corner it's going to be red, and in this corner it's going to be green, and in this corner it's going to be blue. And basically, where if you have something that maps to the thing in the map, the things that are close to it on the map are also going to be close to it in the feature space. So you can actually implement this training on a single slide. We have a little bit of abusive notation here, but forgive me, it does all fit on a slide. And basically the idea is that we're going to have we're going to have an iteration count that we're going to fix, and we're not going to go beyond that iteration count. And we're going to shuffle our training sets so that we process it in random order. And then we have a couple of, in order to prevent the accidental organization of our training data from biasing our map, and then we have a couple of hyperparameters that we care about, both of which we define as a function of the amount of time we've been training. So the first one is the neighborhood size, which controls how much of the map around the best matching unit will be affected by any single example. And the second one is the learning rate, which controls how much the map changes in response to each sample. So these both decrease over time, and at the end of each iteration here, we're updating the map slightly by bringing the area around the best matching unit slightly closer to the example we processed. So I hope that code, at least the sort of high-level, quick elevator pitch for it, is easy enough to understand. It doesn't seem like a super complicated technique. It maybe intuitively makes sense that you'd want to bring things closer to one another and sort of average it out like that. But it isn't really clear how we could implement that code in parallel, right? And in fact, many serial implementations of machine learning algorithms rely on code patterns that are difficult to parallelize. So I want to sort of start by thinking about things that are difficult to parallelize. And why should we care about things that are difficult to parallelize? Well, Amdahl's law, actually, which is over 50 years old at this point, says that if we want to increase the speed of our program by parallelizing it, the hard sort of upper bound on how much speed up we can get is a function of how much of the time in the program we spend actually doing parallelizable tasks. So put another way, the amount of time that you spend doing something serially is a lower bound on how long your program will take to run, no matter how much parallelism you have, no matter how inexpensive your communication is. You can think of a real-world analogy, right? Say you wanted to make a lot of pita bread or some other kind of raised dough that cooks quickly, right? It takes like 4 minutes to actually cook a pita, right? But even if you had a really big kitchen and you were really coordinated and you could flip tens of thousands or hundreds of thousands of pitas every 2 minutes, you'd still have to wait for the dough to rise. And it doesn't matter how big your kitchen is, it's going to take 2 hours to rise that dough. So similarly, we want to sort of make sure that our programs are easy to parallelize so that we can scale them out by adding more nodes or adding more hardware. So one thing to look out for as a sort of warning sign that your algorithm is going to be hard to parallelize is algorithms that shuffle data. This is a problem for a couple of reasons. One is that shuffling is expensive on a single node. It's necessarily not cache friendly, right? But if you're in a distributed system, shuffling everything in a distributed collection might mean that everything has to go across the network to another node. Another problem is when you have an algorithm that you can only specify in terms of updating an intermediate state with a single example. If you're a functional programmer, you know this technique is a fold. And folds are really great and a really expressive way to think about programming, but if you just have a fold, you're in trouble. If you have, on the other hand, a reduce operation where you take two things of the same kind and you combine them together to make a third thing of that kind, that's okay. If you just have this fold operation, though, that's a warning sign that you may not be able to parallelize your code. So one way to sort of fix these kinds of problems is to think about formulating our algorithm in terms of commutative and associative binary operations. If you have operations that commute, it doesn't matter what order you execute them in. If they associate and commute, you can execute them in parallel, you can execute them in any order. As long as you do them all, you'll get the same result. That means that you can parallelize your code. Another example is maybe instead of using an online technique where you examine one example at a time, maybe there's a batch technique that you can use instead that you can adapt to running in parallel by running different batches on different nodes and combining the results. Finally, there are a lot of optimization frameworks that have parallel implementations, like stochastic gradient descent. If you can think about how to formulate a machine learning problem in terms of one of these solvers, you can benefit from an existing parallel implementation. Now, oftentimes it's really easy, or it's relatively easy, to come up with the serial technique, and it's hard to think about how it maps onto one of these. But fortunately, people have done the hard work for you in a lot of cases. There are like a lot of examples of these from many problems that you might be interested in. Either someone's written a paper about it or someone has a library that does this that you can read. So in the next part of the talk, we'll be looking at how this stuff actually happens in SPARC. So I want to just provide context so we're all on the same footing about what SPARC's partitioned collections and compute model look like. The fundamental abstraction in SPARC is called the resilient distributed dataset. This is an immutable, lazy, typed collection. So it's immutable in that if you update the collection, you don't actually update it in place, you create a new collection. It's lazy in that you don't do that until you absolutely have to. And it's typed in that it's a homogeneous collection and you know what's in it. If you have one of these things, you know what's in it. So when you ultimately have to compute those values, your application serializes a function, a closure, and sends that over the wire to all of these worker nodes, each of which holds a partition of this collection. It then operates on those collections and then can return the value back to your application. Now, because we have a distributed system, we're going to have failures. We're going to lose these nodes. They're going to go away. But because we have this immutable data structure that's lazy, we always have a recipe for recreating any part of it that we can just replay on another worker when we spin one up and get the results back. So SPARC also provides a couple of higher level abstractions on top of this low level interface. There's a data frame interface, which is an untyped layer on top of RDDs that has query planning like a database. And then there's data sets, which is sort of, you can think of as combining the best aspects of both RDDs and data frames. So it's a typed interface that also has query planning. We'll talk a little bit more about these in a bit, but I want to talk about how you would go for this low-level RDD implementation now. And the basic approach that I took is I started with a batch implementation of self-organizing map training. And this is something that I figured out after reading the documentation for another library. I didn't even have to read a paper or a code. You just sort of look at this and the documentation explains what happens. And the idea is that you look at all of the examples at once, You figure out how each example would have affected the map, and then you average all of those effects together and produce a new map at the end of each sort of training epoch. So you can do this for batch, and the sort of insight is that the thing you come up with, this intermediate model, is something that you can actually average with other intermediate models. In this case, we could run it on a bunch of batches and produce a model for everything. In fact, we could run it on a bunch of partitions of a data structure and produce a model that reflects the whole data set that we might not be able to keep in memory on a single machine. Now, this isn't always true, right? You don't always have an intermediate model that you can combine in a commutative and associative binary operation, like averaging. And in fact, for this case, you can imagine, if you just sort of think about what we talked about with that self-raising map training, you could imagine a pathological case where you had very small partitions, right? Your partition is 1 or 2 elements, and maybe you would never converge on training because they would just sort of randomly land in different parts of the map. But that's not always going to be the case, and the nice thing about that is it really turns into an engineering problem, right? If you're running machine learning models in production, you have to sort of continuously evaluate and validate them. And it's no different with this, right? This is the kind of thing that you can identify when it happens because it will be obvious. So, something to keep in mind though. So let's look at an implementation template now for taking batch learning algorithms and turning them into parallel learning algorithms that operate on partition collections. We're going to use the aggregate method in the SPARC's RDD API. And what aggregate does is it lets us supply 2 functions. One of those functions is essentially a fold. It takes individual values in a single partition and combines them together in some way to produce a value representing the whole partition. In this case, we're delegating the heavy lifting to another, to this model state class that we're not showing on the slide, but the idea is that you can update the model state with each example you see in a partition, and then you have the intermediate model for that batch, for that partition. The second thing that aggregate lets us supply is a reduce operation that takes the states from 2 partitions and combines them into 1. So this API is sort of convenient because we can think about how we're operating both on values within a partition and the values across partitions. We have both that fold step and that reduce step. This basic template is a really great place to start, but there are a couple of things I want to sort of call your attention to. The first one is that we have a reference to an intermediate model in one of these closure arguments. So remember that when SPARC is actually executing this code, it's going to serialize that closure and anything that you can reach from that closure, obviously, and send it out to these worker nodes. So here, instead of just shipping a simple function across the network to all of your workers, you're going to be shipping this model object, which could be enormous. So not only is that inefficient, but it could cause your program to crash because SPARC has default sort of limits on how big your closures can be that are designed to discourage you from doing this sort of thing. A better option is to use what's called a broadcast variable. So at the beginning, we broadcast, which provides an efficient way to communicate that model structure across our network. We get the value of that broadcast variable, we get a handle, and then we can dereference that handle within the closure, and we've efficiently communicated that. So, and we'll also need to remember to remove that broadcasted model at the end of each iteration. So this points to an important consideration for this sort of thing, whether or not you use SPARC though. You're eventually going to have to be communicating large values across multiple workers, and you need to sort of figure out what the efficient way to do that in your framework of choice is. The last thing I want to call out in this template is the use of aggregate itself. Aggregate is clearly the right interface for what we want to do, but as we'll see, it's the wrong implementation. Let's look at how aggregate works in SPARC. First, you compute that fold step at each of the workers in parallel, but then you ship all of those intermediate models to the application program where they're combined serially. This is a bummer because it increases memory pressure at your driver. I mean, these intermediate models could be very large. If you have a lot of partitions, you could be using a lot of memory in your application. But also, if we think back to Amdahl's law, this is something that's happening serially. We don't want that to happen serially. We want it to happen in parallel if possible. So instead, let's look at a different method SPARC provides, which is called tree aggregate. It has essentially the same interface, but a different implementation where those aggregation steps are performed in parallel at the workers. Combine those results until you just have a few left, and then you send those to the application to be combined in parallel. So the framework that you like to use, or the framework that you wind up using, may distribute aggregate sensibly, right? But I think the important thing to keep in mind is that you might be tempted to think of SPARC as just another Scala library, right? Or with these JVM frameworks as sort of just another library. But the nice thing about functional programming and declarative programming is that you know what's going on if you look at a type signature or if you look at an interface. In a lot of cases, you can, if you want to do something, you can look for a function that has that type signature, right? And you know what you need. In this case, when you have potentially how something executes, you have to, entailed in the contract of the method, you have to sort of think about that as well. And just considering the interface isn't enough. You have to also think about the implementation. So we've just discussed a general pattern for putting these together in RDDs. Now, for those of you who have used SPARC, how many of you really love using RDDs? Love? Does anyone who uses SPARC love using RDDs? Wow. So I actually love RDDs, but I probably shouldn't admit it. Like, RDDs are considered a low-level interface. People who use SPARC nowadays are going to use data frames instead. It's a higher level. It's easier to use. You'll use data frames or data sets. So we want to support those other features. We want to support machine learning pipelines. We want to make this technique more accessible to users. But before we condemn RDDs, I want to talk about the good and the bad of RDDs so that we know what the trade-offs are. I think this code excerpt points to actually the greatest thing about RDDs. Does anyone see what this code is going to do? Mm-hmm. But the nice thing about this code is that it's not going to compile, because I have a collection of strings and I'm trying to multiply it by 3. That might work in JavaScript, but it doesn't work in Scala. So this is actually something I really like because I make a lot of stupid mistakes. And if I have a type system, I'll find out about those stupid mistakes almost immediately because SBT will complain at me, and I won't find out about those stupid mistakes in like 3 hours after my code has been running for a while, or maybe I'm doing something else. So by contrast, if I look at an equivalent data frame program, this will compile and it will eventually crash, right, when it's already running. So I really like type safety for those reasons. Another nice thing about the RDDs is you can run arbitrary Scala, Java, or Python code in these RDD closure arguments, right? By contrast, if I wanted to do something like scoring a model with a data frame, I'd have to declare a user-defined function. It's a little bit of extra work. But being able to execute arbitrary user-defined code exactly as you wrote it is a double-edged sword, right? The RDD will execute arbitrary user-defined code exactly as you wrote it. So if you're doing something pathological, like what I'm doing here, I'm constructing the Cartesian product of 2 very large collections, I'm running an expensive operation, which I'm not specifying what it is, just anything expensive on each of those pairs, and then I'm throwing away nearly all of them, right? This is a terrible, terrible function, but if I were to run something like this through a database query planner, like the one we have for data frames, it would rearrange that program to do the filtering before the Cartesian product, so that we would ultimately only generate the pairs that we care about, rather than generating a bunch of pairs that we were going to have to throw away. Again, another advantage of RDDs is that you can put arbitrary JVM or Python objects in these RDDs. But that's also a disadvantage if we think about this sort of naive way to declare a very small matrix. Let's look at how the JVM actually represents this kind of memory. We're going to have our three objects here. We have an array of arrays. We have class pointers, flags, size, and space for synchronization code. The outer array just has pointers to two inner arrays, and those inner arrays have two elements. Now, depending on how your JVM organizes memory, this might be slightly different, but in this example, for a typical JVM, we have 32 bytes of data and 64 bytes of overhead. And this is pretty bad for this kind of structure. It's much worse for linked structures like a tree map, where you have a lot of intermediate objects at each node of a tree. You're basically paying a lot for this. By contrast, a data frame is going to use an optimized in-memory representation and some cache-aware data structures that you save time. The really cool thing about data frames, though, is that you can use them with SPARC's machine learning pipelines library, which takes machine learning and makes it very simple. This is sort of inspired by similar functionality in scikit-learn, which is a rich environment for prototyping. And what we're doing here is we're setting up k-means clustering on a data frame in just a few lines of code. We're going to set hyperparameters for how we do k-means clustering. How many cluster centers do we want to find? What's a random seed we're going to use for initializing our cluster centers? Where are we going to get the features from? And then we're going to train a model by, train some cluster centers, and then we're going to use that to annotate our original data with the cluster centers for each element. So there are three key interfaces in this library that we need to think about if we want to extend our machine learning technique to work with it. The first one is an estimator, which takes a data frame as input and produces a transformer as output. The second one is the transformer, which includes a model, and this is something that takes a data frame as input and produces a data frame as output. This can either be annotating a model with predictions, or annotating a data frame with predictions from a model, or transforming values as part of a feature engineering pipeline, say by scaling, transforming, hashing in some other way. The last interface we want to think about is parameters, which control the behavior of estimators and transformers. These can be things like model hyperparameters, or even things like the columns in a data frame that we want to get data from to train on. So I just want to give a couple of quick tips for how to use these interfaces. The first one is sort of think about how you're going to organize things. If we have a trait that we can share between our estimator and our transformer, or between multiple things, we can sort of declare our parameters in there and use that parameter interface efficiently. In this case, we're going to declare the width of our self-raising map as an integer. We're going to provide some user-facing documentation for it, and we can also provide a validator saying that the map has to be at least one cell wide. We're then also going to declare some getters and setters for that parameter. And here we have a trait that we can share between an estimator and a transformer. Another nice thing you can do, and this is an example taken from SPARC's machine learning library, is if you have things that you use commonly, if you have a parameter that comes up in multiple algorithms, like an iteration count or a random seed or a feature column, you can create traits for all of those and reuse them. So you can just mix these traits into any class you're going to use. Now, unfortunately, the ones in this example aren't actually public. They're private APIs for SPARC, but it's really straightforward to do this yourself, and it can save you a lot of time and potential headaches if you do it. So these APIs for machine learning pipelines are pretty easy to use, and they form a pretty good place to get started thinking about this stuff. At the most basic level, with an estimator, you need a method to train a model from a data frame. And with a transformer, you need both a method to construct a schema for the data you'll be transforming and to actually affect the transformation by constructing a new data frame with the transformed data. Because we have to actually check preconditions on the schema of the data we're operating on, and because frequently we'll be operating on data that looks like the data we trained on, we can combine the validation and transformation into a single method. And I'm not going to go through this in detail, but basically we're just going to check that our input columns exist, that the input columns have the types we expect, that the output columns don't exist because we don't want to surprise the user by creating a data frame that overwrites something that was in their input, and then we'll make a new schema. And we can use this method both to validate in an estimator and to transform in a transformer. If we use it just for validation, we'll just rely on the fact that none of these assertions fail. If we use it for transformation, we're actually going to use the schema value that it returns. To actually do the training, the nice thing is that if you have an implementation that works on RDDs, you can just reuse it, right? You don't need to do anything special. You can create an RDD from your data frame and use that implementation as part of a machine learning pipeline. And this is actually something that happens in the SPARC library, so I'm not just telling you sort of a cheap shortcut. This is something that people who do this all the time do. So let's talk about some practical considerations now. I'm assuming we don't have a lot of people in here who've implemented SPARC machine learning pipelines before. Anyone done it? Yeah. So when was the first time you implemented a SPARC machine learning pipeline? What SPARC version? The oldest SPARC version you did it for? 2.1. So everyone who's in the 2.1 era, you do not need this tip. But if you've done, I mean, you may have this in other Scala code too, but if you've done machine learning pipelines in the SPARC 1.4 or 1.5 era, you might have some code hanging around that looks like this, where you take a private API in SPARC, in this case, the user-defined type for vectors, so that you can have a vector in a data frame and write a function that operates on it, and you expose it, right? Who has Scala code that looks like this, where you take someone's private API and expose it so that you can write code against it? No one who's willing to admit it, I see. So the nice thing is that these APIs still aren't public, but in SPARC 2.0, starting with SPARC 2.0, they have them exposed in a developer API object that you can rely on if you want. Another thing you might want to do is cache your training data only if it's not already cached. That sort of makes sense, right? Check to see if the data that you're training on isn't cached. If it isn't cached, cache it. If it wasn't cached, uncache it when you're done. So we've looked at ways to improve your parallelism and some concrete suggestions for using ScaleOut parallelism. The last thing I want to talk about, though, is how to improve our single node performance. Because remember that the things we're doing serially really put a lower bound on how much time our program will take to execute. So the last few suggestions I have are related to improving the single node performance of your techniques. We'll look at ways to optimize repeated similarity calculations. We'll look at how to ensure that your linear algebra code executes in a native library. And we'll look at some things to consider if you want to take advantage of hardware acceleration for linear algebra. So many machine learning techniques involve repeated distance or similarity calculations. You might have a bunch of vectors in your model, and you're going to compare each training example to all of those. In this case, we're looking at angular similarity, which we did in the SelfRaising Map example. So in that case, you're going to be calculating a lot of angular similarity. But you're going to need both the magnitudes of vectors and the dot product of vectors. The magnitudes, though, for the vectors in your intermediate model are not going to change during an iteration because the intermediate model is not changing during an iteration. So you can actually cache those. If you hang on to those, when you run a loop with a whole bunch of these examples, you don't want to recalculate that magnitude. If instead I say I'm going to hang on to that magnitude and cache those, you can typically get a pretty good performance speed up from that. Another thing to consider is how often you touch external libraries, like the linear algebra library you use. Each invocation is going to involve either running in the JVM or copying data to a buffer so that you can execute it in native code. And so each invocation might have either a high fixed cost or it's going to be doing arithmetic in the JVM, which is not going to be as fast as you'd like. In fact, a lot of linear algebra libraries for the JVM aren't even going to bother delegating your operations to native code if you're doing a vector-to-vector multiplication, or even if you're doing a bunch of them, right? So if you're doing a bunch of vector-vector multiplications, if you're doing a bunch of dot products, think about whether you can use a matrix product instead, because that's more likely to get sent to the native code that's going to be faster. And there are trade-offs to running in native code, so always sort of profile this and see if the things you're operating on are actually large enough to benefit from running on native code. But if you want to do this and you're using a library like Breeze, which is a popular sort of algebra library for Scala, It can be a headache to set this up and deploy it, but in some cases it's very easy. If you're using Breeze and you're using SBT, you can add a dependency on a library called Breeze Natives, which bundles not only Breeze, but also native libraries and native wrapper libraries so that you can get the benefit from running these on fast native code. Another thing to consider is the kinds of values you're operating on. A lot of frameworks that work on the JVM will encode everything as a double, whether that's a number where you legitimately need 64 bits, or whether it's a small integer, or even if it's a Boolean, right? Imagine a Boolean. You could fit 64 Booleans into a double, right? So think about whether or not this is something you actually want to do. One reason why this is a consideration is that if you have something like a dot product declared in a high-level language, that dot product is going to take about the same amount of time whether you're operating on doubles or whether you're operating on floats. So let's say I make a generic version of my dot product that I can run on any kind of number. I'm essentially going to be paying by the operation there, because the execution time is going to be dominated by control flow, and these operations are going to be happening one at a time. So the doubles are going to have more memory pressure than the floats. They'll be a little slower. They won't be as cache friendly, but I probably won't notice. By contrast, if I want to run this in accelerated native code, where I'm using a function like this function available in SSE4 and AVX that takes the dot product of two vectors that I've represented as many numbers as I can pack into a certain sequence of bits, right? Say maybe I have 128 or 256 bits, and it's how many numbers can you get into that many bits? Well, in that case, if I'm running it on doubles, it's going to be twice as many operations as if I'm running it on singles, right, or floats. So we want to consider that kind of thing and use the smallest, narrowest number type we can get away with if we want to take advantage of hardware acceleration. And you see this with GPUs too, right? There's a lot of people doing work with fixed point arithmetic on GPUs because it can be more efficient. So I want to wrap up now by sort of quickly reviewing what we've talked about today. First, we discussed why you might want to scale a machine learning technique out. I hope that was convincing. We saw that Amdahl's law puts an upper bound on how much speed up we can get based on how much time we spend doing things serially. So we tried to focus on things that we can do in parallel. We discussed some strategies for parallelizing machine learning algorithms in terms of reformulating our algorithms in terms of commuting operations, taking batch algorithms whose intermediate results are amenable to combining with commutative and associative operations, and thinking about our techniques in terms of optimizers or solver frameworks that we already know how to execute in parallel. We saw how developing ScaleOut parallel libraries for SPARC requires us to be comfortable both with low-level APIs and with contemporary high-level APIs, and occasionally to get our hands dirty with private APIs or developer APIs as well. And finally, we considered some techniques for ensuring that our programs run efficiently when they have access to native code or hardware-accelerated algebra libraries. And really, if you take a step back, that brings us back to Amdahl's law, right? Because if we can perform arithmetic on as many values as we can pack into our register, but we have to spend a bunch of time slowly copying it out of the JVM, we want to make sure that we do as many multiplications or operations as we can to amortize out the cost of that copy. I hope you'll leave this talk inspired to scale out a favorite or new technique, but I hope that you'll be in touch in any case. Here's how you can keep in touch. I'm willbe at redhat.com or willbe on Twitter or GitHub. I have a personal weblog at shepho.freevariable.com where I regularly write about machine learning and distributed systems. And radanalytics.io is a community site that my team maintains where we have a lot of stuff for building intelligent applications in a contemporary environment, including a library that contains the SelfRaising Map implementation. Thanks so much.
So, thank you very much. We're going to have just a few minutes for questions, but obviously probably people can follow up later as well.
Yes.
Any questions from you guys? Okay.
Thanks for a great talk, and I have a question related to tree algorithms, so tree map reduce. Is it somehow related to reduce by key operations in SPARC?
Yeah, so so the tree aggregate in the same way that reduce by key, it will do as much aggregation on the worker nodes, on the executor nodes as possible before sending them back to the driver.
Okay. But it's different operation.
It is a different operation, but it's similar in that the work is actually distributed as much as possible before sending results back to the driver. Yeah,
Thanks a lot.
certainly.
Any other questions? I have one, maybe just to sum up. I was wondering if you were talking about MLlib. So how much of the algos there are actually parallelized properly, do you think?
Oh, properly is a strong word. MLlib is great. I think that it's very good for prototyping. I don't know that a lot of people use all of it in production, but I think that it's certainly. I mean, I think what people wind up doing is developing libraries that extend MLlib and fill in gaps and sort of provide their own implementations of things, and that's what my team has done, and that's I think what we hear from a lot of other people as well.
Okay. Right. Thank you very much.